All right, hello everyone. We're going to try to record this over again. I'm having all kinds of problems with this video here. I'm running way late. And welcome to my channel. This is an educational channel. We look at great theories of everything that can benefit you if you learned about them, but you probably didn't because they're obscure. And today is our 440th video on the reciprocal system of theory. And that is originated by Dewey B. Larson. In 1959, Mr. Larson proposed his two fundamental postulates about how he believed the universe operated. They are that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 fundamental aspects, space and time. That is the first postulate. The second postulate is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. The first postulate is what carries the most weight. The second postulate is somewhat questionable and has been questioned by some of Larson's followers. But the second postulate is mainly kind of axiomatic. It's just geometrical and mathematical. But the content is really in the first postulate. Larson says that the universe is made out of motion, not matter, not energy, but motion. And in particular, he's saying that it's made out of a certain kind of motion that's called a scalar motion. Scalar motion is a motion that has a magnitude, but it has no specific direction. You can envision a scalar motion if you take a balloon and with a magic marker you put some dots on it. If you blow up the balloon, all of the dots will be moving away from each other. But they won't be moving in any particular direction. In fact, they will be moving in every direction. All of the dots will be moving away from all of the other dots. And even the locations between the dots will be moving away from each other. It's really like the expansion of space itself, not so much the motion of the dots. The dots are just along for the ride. And that is a scalar outward motion. Larson calls that the progression. Now, if you suck in the balloon and all the dots are moving toward each other, but in no specific direction, that is an inward scalar motion, and that's what Larson calls gravitation. Now, if you arbitrarily decide that one of those dots is going to be your reference point, and then you will arbitrarily say, I pick this dot to be motionless. I assign this to be motionless. Then you can start to impute directions. You can say, well, this dot is moving in this direction toward this reference point. This dot is moving toward the same reference point. This other dot is also moving toward this reference point. It will actually appear as if there is a force field emanating from that reference dot, and that everything is being attracted by that dot. But that will not be the case. Every dot will be moving on under its own, auspices toward every other dot. But since you've assigned one as motionless, you've basically created what Larson calls an as-if force. There looks like there is a force field. It looks like there is an action at a distance and that there's an attraction. But there isn't. Every dot is pursuing its own course. So that is really what you would call an abstraction. You're stopping the world. You're taking a snapshot, you're stopping the motion of this one dot, and then you're watching what plays out after that. And that is abstracting the whole situation. That's what Larson would call a spatial reference point. So when you have this spatial reference point, you have what Larson calls coordinate space. Okay, so you have a 3 dimensions of space in a still frame. You have x, y, z coordinates. These are vectors. So these are all directions. And so you're able to assign a direction by having this still frame, this still reference system or spatial reference system. But in time, you still have they flow, or the progression of time. Time is always getting later and later and later and later, just like it was with the expanding balloon example. Now, just one thing is a little bit different in that this example of the spatial of the balloon, expanding balloon, is really only in 2 dimensions because you're just on the surface of the balloon. In order to fill in that 3rd dimension, you might want to use an analogy such as raisin bread, where it's like the raisins are in the interior of the bread as well, and as you put the bread in the oven and it rises, all of the raisins will be moving away from each other. But you won't be able to determine a direction unless you assign one raisin as motionless, and then you'll be able to impute directions. And that would be more analogous to the 3-dimensional spatial reference system or coordinate space. Now, at the end of Larson's first postulate there, he says that motion is the relationship between space and time. That is one thing that Larson has gained advantage over other people that have proposed a universe of motion, is that they have not redefined motion. Larson defines it as the relationship between space and time. And what you can see there is, you can see, if you take the simplest kind of motion that we know of, speed, the car is moving 10 miles per hour. 10 miles of space in 1 hour of time. Space over time. Speed is space over time. That is a relationship between space and time. It's a fraction with space or time as the numerator and time or space as the denominator. And Larson expands that notion to really cover all of our scientific phenomena, our forms of motion. All of our scientific phenomena are fractions with space or time as the numerator and time or space as the denominator. And then he goes to the next step and he says that space and time are reciprocals of one another. And so you have a reciprocal relationship between space and time. Looking again at motion, the car is moving 10 miles per hour. Well, let's decide to double the speed. You double the speed and you can say the car is now moving 20 miles per hour. But equivalently, you can also say the car is moving 10 miles per half hour. You can multiply the space or you can divide the time. That shows you a reciprocal relationship between space and time in speed. But again, Larson expands that to all scientific phenomena. They are all forms of motion, and they are fractions of space or time as the numerator, time or space as the denominator, such as energy. Energy is time over space. Matter. Matter is time to the 3rd power over space to the 3rd power. And again, in Larson's postulate, he says that space, time, and motion all are in 3 dimensions. So you can have really up to 6 dimensions of space over time, because like for something like density is mass per volume. So mass is time to the 3rd power over space to the 3rd power, but volume is space to the 3rd power. So mass per volume is time to the 3rd power over space to the 6th power. Force is time over space to the 2nd power. Its conjugate is acceleration. Acceleration is space over time to the 2nd power. I dropped the rock out the window and it fell at 32 feet per second per second. 32 feet of space in 1 second per second. Time to the 2nd power. You can also evaluate equations this way. Force equals mass times acceleration. F, force, time over space to the 2nd power, equals mass time to the third power over space to the third power, times acceleration, space over time to the second power. Multiply that out, and you get time over space to the second power, which is force. Force equals ma. You can do that with equals mc squared as well. You can do it with, any other kind of valid equation that you can find. It will always work out. So this is a very good way to check your system, because it's much better than the MKS system, because the MKS system uses 3 variables, including mass, space, and time. But this one is just using space and time. So it's a lot simpler to evaluate. Now, you've got this generalized reciprocal relationship between space and time. And what that basically means is that whatever qualities adhere to one adhere to the other. Okay, so we talked about coordinate space and clock time. That's what we see in our general environment, kind of when we are abstracting or taking reference, the spatial reference system. But if we were in a different environment, then we would observe coordinate time and clock space, 3 dimensions of time in a still frame with XYZ coordinates, or perhaps IKJ coordinates. And we would observe clock space. Space is always getting later and later and later, like on the surface of an expanding balloon. So that's what you would call the temporal reference system. So again, space and time and motion have 3 dimensions. These are really your 3 dimensions of motion. You have your spatial reference system, you have your temporal reference system, and then you have your scalar or natural reference system. That is this outward motion of the expanding balloon, which is a progression in both space and time. And this all kind of comes about through what he calls the discrete unit postulate, which is part of that first postulate. The universe is composed entirely of motion, existing in 3 dimensions in discrete units. So motion, space, and time come only in discrete units. You have to have a full unit of space before you have space. You have to have a full unit of time before you have time. Just like you have to have a full orange before you have an orange. You can't just have an eighth of an orange. Now you can take that orange and cut it into eighths, but then you stopped the whole universe of motion. But in a universe of motion, you only have wholes, quanta. And turns out that 1 unit of space is approximately 1/500,000th of an inch. 1 unit of time is approximately 1.6.5 quadrillionths of a second. And Larson calls that unit speed. Unit speed is 1 unit of space in 1 unit of time. And that is the progression, what he calls the progression of the natural reference system, or this expanding balloon analogy, or the raisin bread analogy. What you're seeing with this progression, or the scalar reference system, is the progression of 1 unit of space in every 1 unit of time. Both of them are progressing 1 at a time, 1 and 1 and 1 and 1. And that is also known as the speed of light. So the speed of light is unit speed, 1 unit of space in 1 unit of time. So that outward movement of the progression, Larson calls that the progression of the natural reference system. And that, if you have a universe of motion, universe made out of motion, you have to be able to conceive of motion without anything moving. Motion precedes the thing that would be moving. So that is your empty universe. The empty universe is the progression of the natural reference system, the motion outward at the speed of light in all directions. And Larson calls that the progression of the natural reference system, or the null point, the 0 point, the neutral point. You could call it the ether, the origin. the zero reference point, the natural reference point, and the source. And so Larson makes his measurements from that point, and at that point, half of the universe is going to be moving faster than that point. Half of the universe is going to be moving slower than that point, because it is the midpoint. The half that's moving slower is the half that we're familiar with. He calls that the material sector. And there you have relations based on coordinate space and clock time. And then the half, and that is well known to scientists, the half that is moving faster than the speed of light is blasphemy to the scientists who think that the speed of light is the maximum speed of the universe. But Larson calls that the cosmic sector. And the cosmic sector has relationships based on coordinate time and clock space. 3 dimensions of time in a still frame, and space is always getting farther and farther and farther apart in no particular direction. Scalar space and coordinate time. And that shows again that reciprocal relationship. You have, when you cross that boundary of the speed of light, you have to invert the roles of space and time. Now, within each one of those sectors, there is an inside region also that has to do with the discrete unit postulate of space and time. So, in less than 1 unit of space, 1/500,000th of an inch, you have atoms and molecules that are interacting. But there's not less than 1 unit of space. So they're not interacting in space, they're interacting in time. Because the universe is made out of space and time, so it's got to be one or the other or both. And if it's not space, then it has to be time. And so Larson calls that the time region. And that is the region of interaction of atoms and particles, microscopic, region. And when you cross that unit space boundary to get to the time region, you reverse the rules. And so in this inside region, the progression is now moving inward and gravitation is moving outward, unlike in the outward regions or in the scalar region. The same is true about the space region, which is within the cosmic sector, which is the unit of interaction the area of interaction less than 1 unit of time. And in less than 1 unit of time, you have cosmic atoms, cosmic molecules interacting, otherwise known as antimatter. And if they're interacting less than 1 unit of time, then they are in what Larson calls the space region. And in the space region, in space, because there is no time, because there's not a full unit of time. And so the rules again reverse, and the progression is going inward instead of outward, and gravitation is going outward instead of inward. Now, you also get atoms out of this system from the source, from the progression of the natural reference system, which is moving outward at the speed of light in all directions. In order to make matter, you have to reverse that progression in a number of different dimensions. First, you turn the progression into photons by, Larson says, by vibrating, using oscillating motion. Other commentators on Larson say that it's from 2 rotating motions. Either way, it forms an oscillating motion or a wave-like motion, which propagates at the speed of light, because that is the speed of the progression. So this wave-like motion is basically on the surface of the balloon. It has no independent motion of itself. That's why it's always measured at the speed of light. And if you take that photon, you couple it with another photon, because geometrically it's just as possible to have 2 photons vibrating around the same central point. And then that 2 photon combination needs to be rotated in 3 more dimensions to basically stop it and reverse the the motion of that outward expanding balloon and turn it into an inward motion, which is gravitation. So gravitation is the intrinsic, motion of something that gets vibrated and then gets rotated in 3 dimensions. And so Larson's periodic table, every element has three numbers corresponding to the primary 2-dimensional rotation, the secondary 2-dimensional rotation, and a 1-dimensional rotation. The 2 first numbers, A and B, they alternate, and then the third number, C, can be positive, negative, or 0. It's 0 in the cases of the inert gases, the noble gas series. Now, you take these numbers and permutate them in various ways to come up with the equations for the basic properties of matter. We're about to start chapter 5 of Larson's book called Heat. So heat, you start with your atoms. Your atoms come to an equilibrium in the time region because the time region, the progression is inward, gravitation is outward. The progression is constant and omnipresent. Gravitation is variable based on the inverse square law, how close they are together. And then when they come to an equilibrium, when both the force of the progression and the force of gravitation are the same, that is the interatomic distance, or the interatomic equilibrium that is established, how far away the atoms are. In the legacy science, the atoms are touching each other. But in Larson's system, the atoms are actually just what scientists call the nuclei. And all the space between them is the packing. It's the equilibrium that they've established between each other. And then heat is going to be is going to add to that gravitational force that is going to be, or the rotational force that's going to be moving all of the atoms away from each other, I believe. But we'll find out. Let's start, read a little bit of this chapter here on heat. We'll see what Larson uses and what equations he derives to figure out heat. If an atom is subjected to an external force of a transient nature, such as that involved in a violent contact, a motion is imparted to it. Where the magnitude of the force is great enough, the atom is ejected from the time region and the interatomic equilibrium is destroyed. If the force is not sufficient to accomplish the ejection from the time region, the motion is turned back at some intermediate point. I guess he calls it V. I'm not sure. I can't quite read that. And it becomes a vibratory or oscillating motion. Now, the time region is for 3 dimensions of the time region are for the solid state. So I guess if the independent motion, which he calls an external force of a transient nature that's involved in a violent contact, if that contact is violent enough, it ejects it from the time region, which means it turns it into a liquid solid, a liquid vapor or gas. If it's not enough to eject it from the time region, then it just heats it up. Okay, so that is the vibratory or oscillating motion. Where 2 or more atoms are combined into a molecule, the molecule becomes the thermal unit. So the thermal unit can be either an atom or it could be a molecule. But the thermal unit, the temperature is measured on a unit by unit basis. That is the discrete unit postulate. Everything in the reciprocal system is measured on a unit by unit basis. There's a unit of motion, there's a unit of force, there's a unit of speed, there's a unit of mass, there's a unit of energy, and so on. And they're all derivable from their space-time coordinates. So your unit of energy is time over space. The unit of energy is, the unit of time is 1.52 times 10 to the minus 16 seconds, and the unit of space is 4.56 times 10 to the minus 8 meters. When you divide those, you get something like 3.33 times 10 to the minus 11 or something like that. And that is the unit of energy. Okay, the statements about atoms in the preceding paragraph are equally applicable to the molecular units. In order to avoid continual repetition of the expression atoms and molecules, the references to thermal units in the discussion that follows will be expressed in terms of molecules, except where we are dealing specifically with substances such as aggregates of metallic elements, in which the thermal units are definitely single atoms. Otherwise, the individual atoms will be regarded for purposes of the discussion as monoatomic molecules. The thermal motion is something quite different from the familiar vibratory motions of our ordinary experience. In these vibrations that we encounter in everyday life, there is a continuous shift from kinetic to potential energy and vice versa, which results in a periodic reversal of the direction of motion. In such a motion, the point of equilibrium is fixed and is independent of the amplitude of the vibration. In the thermal situation, however, any motion that is inward in the context of the fixed reference system is coincident with the progression of the natural reference system, which is inward in the time region. And it therefore has no physical effect because the progression is already maxed out. The speed of light, it's really the speed of light in 3 dimensions, and that is the maximum speed. And so if it's coincident with the progression, that means that it is nullified and it has no physical effect. Motion in the outward direction is physically effective. From the physical standpoint, therefore, the thermal motion is a net outward motion that adds to the gravitational motion, which is outward in the time region, and displaces the equilibrium point in the outward direction. In order to act in the manner described, coinciding with the progression of the natural reference system during the inward phase of the thermal cycle and acting in conjunction with gravitation in the outward phase, the thermal vibration must be a scalar motion. Here again, as in the case of the vibratory motion of the photons, the only available motion form is simple harmonic motion, a wave-like motion. The thermal oscillation is identical with the oscillation of the photon, except that its direction is collinear with the progression of the natural reference system, rather than perpendicular to it. However, the suppression of the physical effects of the vibration during half of the cycle, in which the thermal motion is coincident with the reference system progression, gives the motion the physical characteristics of an intermittent unidirectional motion, rather than those of an ordinary vibration. Since the motion is outward during half of the total cycle, each natural unit of thermal vibration has a net effective magnitude of 1/2 unit. Okay, so since the inward motion is canceled by the fact that it is coincident with the progression of the natural reference system, the motion itself is intermittent, meaning that it's moving outward and then it's not moving, and then it moves outward, and then it doesn't move. Like each unit of time, it's vibrating. Each unit of time is going in and out and in and out and in and out. But the in is canceled because it is coincident with the progression. So it's going out and then it's not going. Then it's going out and then it's not going. Then it's going out and it's not going. So that is an intermittent, what does he call it? Intermittent unidirectional motion rather than those of an ordinary vibration. Okay, we're going to try to do one more paragraph here. Inasmuch as the thermal motion is a property of the individual molecule, or the unit, not an aspect of a relation between molecules, which is what legacy science says. The factors that come into play at distances less than unity do not apply here. And the direction of the thermal motion in the context of a stationary reference system is always outward. As indicated earlier, therefore, continued increase in the magnitude of the thermal motion eventually results in the destruction of the interatomic force equilibrium and ejection from the molecule, the time region, ejection of the molecule from the time region. It should be noted, however, that the gravitational motion does not contribute to this result, as it changes direction at the unit boundary. So the escape cannot be accomplished until the magnitude of the thermal motion is adequate to achieve this result unassisted. Okay, and then when it does achieve that result, basically you move into the liquid state, or at least one of the, could be, I guess, the vapor or something, but really that would be the melting point of, and when it moves completely out of the time region, then it would be a gas, because there are 3 dimensions. So a solid is 3 dimensions in the time region. A liquid is 2 dimensions in the time region and 1 dimension in the outside region. Vapor, 2 dimensions in the outside region and 1 dimension in the time region. And a gas is completely out of the time region. That's how I understand it anyway. And we'll see if we can dig into this a little bit more tomorrow. Just don't get confused, or, if you are confused, don't worry about it. We're going to just get the big picture, and then we're going to do detective work to uncover more. So thanks for tuning in today.